Welcome back to Mr. Lamb Science Corner. I'm not sure in what order we're going to be putting these up, but somewhere we just shot another video on Galileo, and I'm not sure if this is going to be before this or what. We'll find out. But anyway, speaking of Galileo, I did the thing where it showed that two objects fall at the same rate, and I said that it was probably false that he took two balls of different weights up to the Leaning Tower Pizza and dropped them. But what he did do is he rolled balls down inclines. And so I thought we'd talk a little bit about rotational inertia and not just regular inertia. So I have here 3 cans of Campbell's Best. One is bean with bacon, another is beef broth, and the third was chicken with rice. Now, what they have in common is that they all weigh about the same, pretty close, and they're all the same size cans. And so in terms of rolling, we're not going to have like a big ball, small ball kind of problem. They should roll at about the same rate if everything else is held constant, which it's not. Because the bean with bacon is solid inside. So as it rolls, everything's going to be turning. Okay? The beef broth is liquid. Okay? It's all liquid inside. So as it rolls, the can is going to have to turn, but the liquid inside is not directly connected to the can. So as the can rolls, the liquid is going to basically stay in the same spot, and the can's going to roll, but the liquid is not. Okay? And so the mass that's going to be turning is going to be considerably less for this than it is with bean with bacon. The chicken with rice is going to be somewhere in between, and maybe even a little bit one way or the other, because it's liquid mostly, but it also has some solid. It's got some chicken in it, and it's got some rice in it. That's why they call it chicken with rice. And so as it turns, the can is going to rotate, and the liquid is not, but the solid is going to sit down here, and it's going to cause some friction with the can as the can rolls. And so we'll see what happens when we do that. So rotational inertia, let me do this. Rotational inertia is different than regular inertia because the inertia is measured by the mass. The more massive an object, the more inertia it has. Okay, so, and we're all pretty familiar that if we want to push a bowling ball down the alley, that takes a certain amount of energy, and if we want to push a car, that's going to take a lot more. Okay, so if we're talking about pushing something, the more massive an object, the more inertia it has, the more resistance. And inertia is the resistance to change in motion. If you're pushing a grocery cart, there's a big difference between one that's fully loaded and one that's empty. Whether it takes more to get the fully loaded cart going, and once you get it going, it's harder to stop it. It takes more energy, and it takes more energy to turn it, because all of those are changes in motion. Starting, stopping, and turning are all changes in motion, and the more inertia you have, the more mass you have, the more energy it takes. Okay? So rotational inertia is different though, because it matters not only the mass, but how the mass is arranged, I guess we'll say. And we're all familiar with this because if you never did, your kids certainly can show you how if you're spinning and you have your arms out here like this as you spin around, which I'm not going to do because I'll probably fall down, and then you pull your arms in here like this, all of a sudden you speed up. You go faster. And if you're going faster, then you put your arms out like this, you slow down. Your rotational inertia, less consideration of friction, is the same whether your arms are down here like this going fast or out here like this and going slow. rotational inertia is conserved the same as regular inertia is. It takes some energy. So what we're going to do is we're going to have a race. We're going to take the bean with bacon and we're going to race the beef broth, and we're going to see what happens. Now remember that even though the mass is the same, the beef broth has less mass turning than the bean with bacon. Okay, so I set them here like this, and they're probably going to fall off the board because that's what they do a lot. And so we go ready, set, and we see that the beef broth won. Okay? And notice the high-tech part here. I have a board. This is my shop, obviously, and I happen to have a board handy. You can get one too in cans of soup. Okay? Now let's race the two liquidy ones, the beef broth and the chicken with rice. Okay? So get there. This is the chicken with rice. And the beef broth won again. Now when you get through with this demonstration with your students, you have two choices. You can take the soup home and eat it, or you can leave it on the shelf for years. Eventually the soup becomes not so good inside, but it'll stay as a can and do this demonstration till the end of your career. Your choice. Okay, so let's try bean with bacon and chicken with rice. And they were just right at a dead heat. Remember that the liquid, even though it would go faster because of the friction inside, it went slower, so it turned out to be about the same speed as that as the bean with bacon. Okay, rotational inertia, I certainly would not get involved in any math. It's a high school subject, and I will tell you the high school students really don't like it because it's really interesting. College students, if they're not physics majors, don't like it either. So certainly stay away from the math, but you can certainly refer to the kids spinning around, and don't be surprised on the playground if they're doing that at recess, just to check things out. It's a fun thing to do. You may want to ask kids what they think is going to happen beforehand, have them notice that the cans are the same size. If you want to do two different balls of different sizes, there's a number of things that you can do to get this idea of rotational inertia being different than regular inertia. And quite frankly, I think I would combine the two. I would talk about regular inertia at first, show them how the paper falls at the same rate, take a book and an eraser and drop them. There's all kinds of things you can do, and then I think I would bring in the rotational inertia and tell them, says, kids, we're going to have some fun with this, and we're not going to do any math or anything like that because it's really quite complicated. Okay, with that, thank you very much. See you next time.